Hi, I'm Juan Loaiza, and I'm excited to talk to you about breakthrough blockchain technology for the enterprise. So first, let's talk about what you need to know about crypto-secure data management, why you need it. Conventional data security technologies focus on keeping criminals out. It uses things like passwords, access control, encryption, etc. Blockchain adds another layer of data security on top of that protects data from being illicitly modified or deleted. It uses things like cryptographic digests, cryptographic signatures, and distributed systems to implement crypto-secure data management. Now, according to Deloitte's Global Blockchain Survey, blockchain is a top 5 strategic priority in 2020 and continuing. However, blockchain projects have notoriously high failure rate. IDC says that the technical complexities are often seen as a barrier. So to realize the promise of blockchain, it needs to be much easier to implement, which is exactly what we've done. We've created a blockchain that can be used for the masses. Up to now, blockchain has mainly been used to develop decentralized multi-party applications. And blockchain required new applications, new development methodologies, new data management products, and new business processes. Now, Oracle has released breakthrough technology that deeply integrates blockchain into the Oracle database. This makes it possible to implement blockchain in mainstream enterprise and government applications with minimal application changes. And it provides the full functionality of the world's leading database on crypto-protected data. The benefits of blockchain are now available beyond decentralized multi-party applications. So Oracle Blockchain focuses on preventing illicit changes to data that records important actions, assets, entities, and documents. So things like contracts, property titles, payments, transfers, ledgers, and account statements. Data that must be preserved and never modified, and data that can be deleted only when it's obsolete. Illicit changes to important records can have dire consequences. For example, loss of assets, legal exposure, loss of reputation, etc. Oracle Crypto Security is not limited to providing change ledgers. It also can directly protect the reference data as well. There are 2 unavoidable problems with existing security technologies. The first of these unavoidable problems is hackers. What happens if a hacker finds a way to bypass the security mechanisms? And obscure new security breaches are discovered all the time. The second unavoidable problem is users who are corrupt or compromised, and they use their valid credentials to make illicit data changes. So these are things like rogue insiders who are corrupt or malicious, compromised users where criminals impersonate them after stealing their credentials, or corrupt enterprises or government agencies that intentionally change records to steal assets or commit fraud. Now, in 2020 alone, there were over 2,700 critical security vulnerabilities. So these hacker vulnerabilities are for real. Also, insider credentials are stolen all the time. They're stolen in enterprises, they're stolen even in things like high schools. Corrupt insiders are well known to steal data and money by falsifying data records. Also, phishing of insiders is an unavoidable problem. For example, hackers gain access to Sony's network after a series of phishing emails aimed at their systems engineers and network administrators. And to break in, criminals even will bribe insiders. For example, there was a recent case where a Tesla employee was offered over $500,000 to insert malware into the Tesla system. And fortunately, he turned them in instead of inserting the malware. So although we can never eliminate security vulnerabilities, we can limit the damage that they cause. And this is what blockchain does. Blockchain does not prevent your data from being stolen, but it does provide an additional layer of defense that could prevent your data from being changed. For example, which would be worse? Someone seeing your bank account or someone stealing the money from your bank account. So Oracle provides protection for many types of illicit changes using the blockchain technology. And I'm going to go through these one by one in a minute. These technologies can be adopted incrementally to protect against the kinds of illicit changes that are most important for each use case and application. And they require very little changes. The only one that requires significant changes are protection against end user identity attacks. Now, in this presentation, for simplicity, I'm going to highlight the primary attacker for each protection technology, but it's not limited to just that one attacker. So let's go through the use cases one by one, these 4 use cases, starting with preventing illicit changes by insiders by using a new technology in Oracle database called immutable tables. So the idea of immutable tables is to prevent illicit modifications by insiders that use the database. For example, changes by rogue employees or employees whose credentials were stolen. And the way it works is by disallowing all database interfaces that modify data in an immutable table. New data can be added to an immutable table, but existing data cannot be changed or deleted by anyone using the database, even database administrators. And a side benefit of immutable tables is that it prevents accidental changes due to human errors. So how do immutable tables work? You create and insert only immutable table by simply adding the immutable keyword to the table creation statements. Immutable tables allow normal relational data, but it also allows documents like JSON and logs. They're not restricted to ledgers. They can store reference data. Immutable tables behave like any other table in the database, except that the immutable table users cannot update or delete rows, change the table definition, convert the immutable table to a regular table, or modify the table metadata. Using immutable tables requires no application changes, and immutable tables are available in Oracle Database 1911, 21.3, or future versions. Second use case, let's talk about detecting illicit changes by hackers by using cryptographic data chaining. So what happens if a database software that enforces immutability is bypassed? And it can be bypassed, for example, by a hacker that discovers a new security vulnerability in the system, or by a rogue or compromised system administrator who uses OS credentials to modify or bypass the database software. We call that an inside hacker. Now, the way blockchain works is it detects changes to data by computing and safely storing a small cryptographic digest of the data. If the data is changed, then the cryptographic digest of the changed data will differ from the previously stored digest. This detects illicit changes even if attackers take over full control of the OS or database. So how does blockchain table work? Again, it's very simple to use. A blockchain table is basically an immutable table that automatically chains new rows to existing rows cryptographically. And you create a blockchain table by simply adding the blockchain keyword to the table creation statement. So as rows are added, they have a cryptographic digest put into them that is a digest that is computed from the new row plus the digest of the previous row, which is chained to all the previous rows. So any modification to data in the chain of rows breaks the cryptographic chain, and therefore you detect the change. Now, how do you verify a blockchain? It's very simple. You either call the verify rows procedure in the database, or you can also independently validate the blockchain without depending on the database, because we use open standard cryptographic algorithms. And so users can read the chain data and verify the crypto digest from outside the database. Also, an independent data auditor can validate the data. It's like a financial auditor validates accounting records. This relieves end users from the task of validating the data and preserves data privacy across users, since only the auditor validates the chain, and therefore only the auditor has to see all the user's data. So immutable and blockchain tables are super easy to use because they're part of Oracle's converged database. They're a feature. This is in contrast to blockchain-only databases like AWS QLDB. They require no application changes. They're accessed using standard declarative SQL. They get full analytics and transactions provided by the database, and they benefit from all the scalability and availability technology of the database, including rack scale-out clusters and DataGuard geographic disaster protection. And blockchain and immutable tables are free in all database editions. Next use case we'll talk about is detecting a cover-up of illicit changes by authorities. And this is done using distributed publication of a data digest. Okay, so cryptographic chain of rows is great, but it can be compromised via large-scale cover-up. For example, when rows are illicitly changed and then the entire chain that comes after the row is rewritten to cover up the change. Examples of a large-scale cover-up include an order is given by a corrupt executive or government authority to replace the entire database, or a sophisticated cybercrime organization deletes and rewrites all the database or table. Now, how do we detect this? To detect the cover-up, Oracle enables the cryptographic digest of a table to be freely distributed publicly. The digest is cryptographically signed by the schema owner of the database to ensure that it cannot later be claimed to be a fake. This is called non-repudiation. The digest can be distributed periodically or whenever important data is inserted. And authorized users of the database can validate that the digest chain is correct and includes the recently inserted data, as we talked about before. Since the digest itself cannot be used to infer the actual data, it's completely safe to publicly distribute it anywhere. So you can distribute it, for example, by posting it to an independent public store or blockchain, or just sending it out via email or REST API. Now, to detect a cover-up, it's very simple. You compare the previously published digest to the current table contents. If they differ, illicit change that was made. Distributing the digest publicly across multiple independent services, for example, email, REST, or Ethereum, prevents an authority or cyber attacker from being able to delete all the independent copies. They'd have to breach all these independent data services. This kind of heterogeneous distribution provides stronger protection than any homogeneous distributed blockchain. And publishing the data digest requires no application changes, so it's super easy to adopt in existing applications. The final use case is preventing data falsification by impersonators using end user data signing. So the thing that we're protecting here is against inserting new data falsely under an end user's name. So an example here is an insider that uses internal information to impersonate an end user, or an end user's credential are stolen by a hacker who then inserts data in their name, or a developer, operator, hacker bypasses the application's credential checking and inserts data as the user. To address these vulnerabilities, Oracle allows end users to optionally cryptographically sign new data that they insert. Now, doing this cryptographic signing requires users that are sophisticated and have a digital identity and public certificate. So it's more common for business to business users than consumers. It also requires applications that implement the data signing. So how does the data signing work? The end user signs the data using their private key that is never passed to the database. Each end user registers a digital certificate containing their public key to allow the database to validate the signature of the data and that the data is correct. The certificate ID is recorded in every row, so we know who signs each data. Oracle can countersign the new data and return that to the users to allow end users to ensure that their data was actually received by the database. This is kind of a crypto receipt for the new data, and it prevents things like a middle tier from filtering certain data to prevent it from being recorded. So those are the use cases. Now let's talk about how this compares to peer-to-peer blockchains. So first of all, a blockchain table with a publicly distributed signed digest is a distributed blockchain, but not a peer-to-peer blockchain. And because of this, it's simpler to use and has many of the benefits of a peer-to-peer blockchain. Blockchain tables prevent illicit changes that are made using the database, and they detect illicit changes that bypass the database. So the gap here is preventing changes that bypass the database. Directly preventing all forms of illicit changes provides stronger protection. However, even if you can just detect illicit changes, this indirectly prevents most fraud. And the reason for this is that criminals won't commit fraud if they know they will be caught. And blockchain always detects illicit changes. So an example here is, for example, a criminal won't take a bribe while being video recorded. Well, blockchain is a kind of video recording for the data in the database. Okay, if you really want to prevent illicit changes that bypass the database, this requires a true peer-to-peer blockchain architecture that uses a consensus-based multi-party agreement for every change. Now, peer-to-peer consensus prevents the takeover of a single database from compromising the entire system. However, even a peer-to-peer blockchain is still vulnerable if there is a common bug across all the peers. Now, peer-to-peer consensus requires new application development methodologies. Also, achieving consensus requires major changes to business processes and how businesses interact with customers and partners in order to achieve consensus on every change. And consensus isn't free. It's not just complicated. It requires sacrificing autonomy and privacy. All the peers have to agree, and all the peers have to see all the data. So overall, peer-to-peer provides very, very effective illicit change prevention, but it comes at the expense of significant complexity for mainstream use cases. So let's talk about use cases for blockchain in the Oracle database. So because Oracle makes it so easy to adopt blockchain technologies, it's now usable in every industry and in a majority of applications. For example, blockchain can be used for financial data like accounting, assets, payment, and insurance, for logistics data like supply chain, shipments, recalls, for education data to record things like degrees, certifications, professional history, government data like legal, trial, permits, citizenship, titles, and all sorts of corporate data like invoices, payments, contracts, employee records, and intellectual property. There's no limit to how blockchain can be used, and it's very easy to adopt. Blockchain is part of Oracle's end-to-end security. Oracle provides conventional password and privilege protection, but it also provides a unique maximum security architecture. And the maximum security architecture has features like database firewall, which provides deep monitoring of database messages to the database. It provides database vault, which prevents administrators from accessing app data at all, so they cannot see the application's data. It provides things like label security and virtual private database that provide database enforced row-level security. And of course, it provides transparent data encryption for all data at rest. And it provides data redaction, which obscures sensitive data that apps should not see when it's returned to the application. In addition to the features inside the database, Oracle also provides a data-safe cloud service, which provides security assessment, monitoring, and auditing as a service across all your databases. And it provides Key Vault, which manages the encryption keys and their life cycles. Now, blockchain is just one feature of the Oracle Converged database that supports all leading-edge database and workloads, which makes it dramatically simpler for developers and administrators. So in addition to blockchain, Oracle Converged database natively implements JSON data. It natively supports microservices, spatial data. It natively implements machine learning inside the database. It provides event processing, CI/CD, graph analytics, REST APIs, and text data. All these are completely integrated and simple to use in the Oracle Converged database in addition to blockchain data. So the key takeaways are that blockchain in the Oracle database addresses real-world data protection challenges faced by enterprises and governments. It prevents illicit insider changes. It detects illicit hacker changes. It detects authority-ordered illicit changes, and it prevents impersonator data fraud. And Oracle Blockchain is a free feature of the Oracle Converged database. You can deploy it with no changes or minimal application changes, so it's super easy to use. For more information about blockchain, you can see our blog, hands-on lab, or documentation. Thanks for joining me today.